This is Knight section 4.1. Now he's going to put everything from chapters 1, 2, and 3 together. So here's a situation. We have some position vector at some time t. And just a little bit later, here is the same particle at some time t plus delta t. And we know how to construct the average velocity from here to here. That's v average, which is a vector, is r at t plus delta t minus r at t over delta t. Now you can break this equation down into components. If you break it down into components, what you get is these two equations. And you can also do the same thing that we did, which is imagine looking at this for a shorter and shorter and shorter period of time. If it's an extremely short period of time, then the velocity won't have changed much. We capture that idea that the velocity hasn't changed much by erasing the average symbol here and putting a limit delta t goes to 0 here. And we do the exact same thing here. And using all those concepts from chapter 3, another way to write this is that v at time t is vx of t times I hat plus vy of t times j hat. This is my velocity vector. Another thing I can do from the chapter 3 is I can label that angle theta. I can say that this length here, the length of this velocity vector, I'm going to call that v. Be real careful here. The velocity vector is v. The length of the velocity vector is v without the vector sign over it. Length, vector. This thing here we call the speed. And now we have some interesting new relationships thanks to the trig. This is always a positive quantity. By definition, the square root sign gives you the positive square root of the whatever's inside of it. And so this length here is always positive, regardless of whether or not the vector v is in the second quadrant or the third quadrant or even the fourth quadrant. When we're speaking about this, we say that this is the velocity and we say that this is the speed. And this comports with the English use of the term. A cop will never say, I'm giving you a ticket for going minus 75 miles an hour. They're going to say, I'm going to give you a ticket for going 75 miles per hour, whether you were coming at them or whether you were going away from them. I'm going to attempt to be very careful. Yell at me if I screw up. Speed is a positive quantity that is the length of the velocity vector. And the velocity vector can have positive or negative components. The next thing that Knight does is he introduces, or reintroduces, since we did have it back in chapter 1, the average acceleration. So here we have the average acceleration. That's equal to v at t plus delta t minus v at t divided by delta t. And you know where this is going. We're going to imagine looking at the acceleration over an extremely short time period where the acceleration itself has not had time to change. And once we do that, then we have a of t is equal to the limit that delta t goes to 0 of that combination. And of course we have a formula for ax of t and a formula for ay of t now. Go ahead and compare those with Knight. Those are equations 4.9 and 4.10. The next thing that Knight does is a little tactics box and reminder of how to compute acceleration graphically. So this represents something going that way. Okay, now just a little bit later, maybe I'm going this way, okay? So here I am going this way a little bit later. So this could be v sub 1 and this could be v sub 2. And we see that in order to calculate the acceleration, we need to calculate v2 minus v1. We need to divide all that by delta t and take the limit that delta t goes to 0. But the really important thing here is that we need to take the difference of v2 and v1. And in Tactics box 4.1 on the top of page 83, Knight talks about how he does that difference. And the way he does that difference is he takes the vector v1 and he flips it around, okay? So he takes this vector and he flips it around to make minus v1. So there we have minus v1. And then he copies minus v1 up to here. Okay, so now minus v1 is looking like that. And then he says that the vector that he's looking for, which is v2 minus v1, is this combination, which is that. Now, I've been teaching it to you slightly differently, and I frankly like mine a little better. My way is that you take v2 and you copy it over here so that its tail is on v1's tail. Okay? And then you draw the vector that goes from v1 to v2, and you end up with that. And of course, that's exactly the same thing I ended up with just a moment ago. However you do it, you get v2 minus v1. I personally find taking their tails, putting them together, going from the one that's negative to the one that's positive to be the least error-prone way of calculating the difference of two vectors. And now we're going to close out chapter 4. Knight's going to go back to the incredibly important special case of constant acceleration. In other words, a sub x, instead of being a function of time, is just going to be a constant. And a sub y, instead of being a function of time, is just going to be a constant. Now, if a sub x is a constant, that means that v sub x is a linear function. It's v sub x of t is equal to some constant, which I'm going to call v naught, plus a sub x times t. V sub x has the interpretation of being whatever vx of t was at t equals 0. And ax is the slope, so it's the intercept and the slope that we've got here. Ditto for vy of t. If the acceleration in the y direction is a constant, then this is a nice way of writing vy. I see I left something off. We now have a v naught x and a v naught y. Now, if this is the formula for vx of t, we already know how to get the most general solution for the position from that. X of t is equal to x naught plus, there's a term that's due to the initial velocity, and then there's a term that's due to the ax. Ditto, y of t is whatever y was at t equals 0, plus v naught y times t, plus 1/2 ay t squared. Now, if you don't want to take the initial time to be t equals 0, you have to generalize this slightly, okay? So this doesn't really gain you all that much, except that in some problems it's kind of convenient not to have the initial time to be 0 in case something happened earlier and you want that time to be 0. Okay, so now I want you to compare that with Knight equation 4.11, and you'll see the only difference between the way he wrote it and the way I wrote it is everywhere I wrote t minus t initial, he called that delta t. So this is the way he has it, delta t squared, delta t squared, and delta t. I must say this is a lot, right? 4.1 is a lot, but the idea was that you've been prepped for 4.1 by chapters 1, 2, and 3. But in a way, 4.1 is almost a summary of everything that has happened so far. And now, in the rest of chapter 4, we're going to use that for a bunch of different examples of two-dimensional motion.